All right, welcome everybody to the third Punch Sandbox. We're really excited to show you some great new data. I'm going to go ahead and put the agenda in the chat. There it is again. We will, as we have speakers, please feel free to raise your hand, ask questions, and put questions in the chat. While we're having our presentations, probably it's best that you both mute and turn off your camera to save bandwidth. But I would encourage you, especially when we're having our discussions, to turn your camera back on when you're talking, etc. So with those logistics out of the way, I'm still seeing quite a lot of popcorn popping. So let's give it another minute. Great to see so many people. Give it another minute. And Craig, why don't you go ahead and load up your talk, since it'll take a minute for it to deblur probably. And one more time, I'm going to put the agenda in the chat, and then I think we're ready to go. Okay, so our speakers, we have Craig is going to talk about the mission. We have Marcus is going to talk about the data, and Chris is going to talk about ways you can access and visualize. Then Ritesh and Dave Webb are going to talk about CME tracking, JMaps. I will very briefly give you a quick and dirty way to make some movies with punched data. We're using JHelioViewer, and it's really actually very powerful for doing comparing to other observations. And then we have the last hour we're planning to be completely freeform. Ask us any question and see how we can help you with the punch data. So without further ado, let me hand it over to our PI, Craig DeForest.
Oh, thank you, Sarah. Glad to be here. Glad to see so many folks coming, and I guess more folks are joining. I'll remind folks, especially those who are joining here after the top of the hour, we are recording this meeting, so bear that in mind. This is a status of Punch. We've been flying for a little over a year. It's been an amazing year. I just want to recap where we are, what we're here to do. Right, we have 4 spacecraft that are working together as a single virtual instrument, the size of the planet. All the spacecraft are working nominally right now, which is somewhat amazing. We've had, knock on wood, only a very small number of very minor anomalies over the course of the mission. One of the things we're paying the most attention to is GPS degradation, which is over the parts of the Earth where you might imagine GPS would be degraded. So it's not from the spacecraft themselves. The 4 spacecraft orbit the Earth. They rotate so that the instruments are facing out toward deep space all the time, and they operate synchronously, and we merge the data here on the ground. Science operations started, depending on how you count, the 21st of May or early June of last year, and we achieved our nominal constellation position in early August. So we've been operating since then continuously. Downlinking more or less 1 image per minute from each spacecraft. Let's see. Data are still preliminary because these are extremely challenging data to analyze. We're doing the challenging part and handing the results of the fruits of that labor off to the community. Once again, most of the people on the call have seen this many times. A few may not have. These are our science objectives. We have 6 of them. The 2 major objectives organized by 6 topics. And whoops, I thought I had a breakout slide there. We have 3 topics that are about the ambient solar wind. How does the sun generate the solar wind routinely? And 3 that are about the transient solar wind, coronal mass ejections, shock dynamics, and CIRs, or stream interaction regions. This is an old slide, excuse me, that should be an SIR at this point. We have 1 working group for each of these major topics, and you can find out who the leaders are from the documentation around, or hopefully we'll get a chance to introduce them. And you can reach out to those people for those topics, or to Sarah or to me in general, and we'll send you the right people. A reminder, this is what our data should look like in the end. This is a simulation that's been forward modeled before launch, showing a CME propagating across the solar system that shows the overlapping fields of view as the spacecraft orbit the Earth and observe from different position angles. Inner limit of the whole constellation is 6R sun. Right now we're achieving about 15. The limit for 4-minute cadence is 80 R suns, and then the constellation as a whole sees out to 180 R suns. That's 45 degrees from the sun. We deliver 4-minute cadence data products with trefoils and 32-minute cadence products with the entire field of view filled in. So we've had a lot of milestones this year. We launched last March 11th. We got first light April 14th, so we're not quite a year since first light. We started our routine science observations on May 21st of 2025, although the constellation was not yet formed, so those were still preliminary. June 9th, we were able to show off our first HALO CME tracked from the Earth, from the sun to the Earth in Anchorage. August 8th, we arrested the drift of the constellation and achieved our nominal science condition. We started releasing new versions of the data in early August as we refined the pipeline. Initially, those were every couple of weeks, or I guess the first couple were a week apart. But as the pipeline has grown more sophisticated, it has taken longer for each release, and that's to be expected. Our first bi-monthly telecon was August 21st. In September, we started tracking comets and realized that was a major unexpected piece of punch science. Version G came out in September. We had Atlas we tracked. We downlinked our 500,000th image from space on October 15th. Released version H data at the end of October 28th. Each of these was a marked improvement over the data before. The 30th, we had our second bi-monthly meeting. We released version I in early December, just before AGU. And then we released the version J data in February. That's what many of you may have been working with. On the 11th of March, we downlinked our 1 millionth image from space. And just a couple of days ago, we released the version K data, which I think are going to knock your socks off even more than the prior versions have. And today is April 2nd, so we are here now. These are just a few of the sort of highlights through the year. There's been a lot more events than this, of course. Publications so far, we have over 15 refereed publications since launch. That is remarkable considering the data haven't been in the final form yet. We have not yet released our final version of our data, version 1, which we expect will be sometime this spring. We do have over 50 presentations and talks recorded in the spreadsheet. I'm sure there are more. We released over 30 punch news nuggets, and this is our 11th iteration of the preliminary data processing. And again, this is a hard problem to solve, and this is expected that we would iterate like this. We're taking the approach that we'd rather release what we have and let people use it for what they can than wait until it's perfect. So that's why there have been 11 so far. Get ready for Punch 7. That's coming up May 12 to 14. We will have results from analyzing version J and K data, discussions on how to reduce the data further, and planning for upcoming science. We will have, I believe, a planetarium dome set up. Either we couldn't get Fisk Planetarium, they're undergoing renovations, but I believe we'll have an inflatable dome available for people to view punch data in. So you can see punch data in a way that really God intended them to be seen. The registration link is at the Punch website, so you can register there if you haven't already. And there will be a few extra surprises for those who like models. these are the data as we saw them at AGU. This is version I data. You are seeing a 90-degree field of view, and I call this movie the pageantry of the cosmos movie because you can see so much in it, right? There's comets, there are planets moving around. The SOC have placed constellation markings on this movie just to give you a sense of scale. Because we've had difficulty analyzing the NIFI data, we are using C-core data here at the center just as a placeholder. We've made progress on that, but the main reason I want to show this is to give you a sense of where we have been in the data processing. Preliminary polarimetry, this is using the version J data, shows that yes, there is something to see there. It's not quite ready for quantitative analysis yet. When we release the version K polarization data, hopefully in the next week or two, they'll be as much better than this as the clear data are, better than the last movie you saw. We have already demonstrated feature tracking that's starting to be incorporated into the pipeline. Thanks very much to Raphael Atier, who vetted the different methods and produced a great demonstration at AGU that we are, again, now rolling into the pipeline. So moving back to that movie that you saw if you came to the AGU or have looked at almost any punch material since then, this is what you've been seeing. This is what we have now. This is version K data. And it is sufficiently different in character that it should knock your socks off. This is a slightly different time interval. This movie was produced just a few days ago by the SOC, but these data are available now at the STAC. The pipeline is chugging through the back catalog. We're expanding from the days right around September 20th in both directions, forward and backward in time. These are the first data where you can see clearly the structure of the outer corona and the Alphane zone, about a factor of 10 to 30 brighter than the residual backgrounds. At this point, we've peeled back enough layers of the onion that you can see effects that weren't visible in earlier versions of these movies. In particular, you may notice these circular anomalies as the moon goes by. That's glint off the optics. That's not to say the optics glint badly. They are extremely good. It's just that we have now drilled away or peeled away enough layers of background light that you're beginning to see every single imperfection in the optical train. So this is what we're going to be talking about later today. If you are paying attention, your socks probably came off. This is an astonishing view. The stars have been suppressed by about a factor of 100. The fact that you can see magnitude 1, 2, and maybe down to about 2.5 stars as bright dots in the field here doesn't mean that we didn't suppress those stars. It's just a measure of how much brighter they are than the background. We have been pumping the contrast high enough that you could see the corona well, and that meant that the brightest stars, the ones that remain on the screen, have been saturated in the movies. So now we've suppressed the star field enough that only those brightest stars remain. And of course, work is ongoing, but this is just a phenomenal step forward and really shows that, yes, in fact, the SOC is delivering on their promise. So kudos to the intrepid SOC team. That's Marcus Hughes, Sam Van Kooten, who's done a tremendous amount of work on how to identify and remove various types of stray light that we didn't anticipate before the mission launched. You may hear about it a little bit later, but we have a much more sophisticated stray light removal pipeline than we anticipated at proposal. And the fact that it works is a testament to the ingenuity and diligence of the whole SOC, but Sam in particular, in really nailing that. We have Chris Lauder, who's been working on equally diligently on characterizing the point spread function of the optics based on the star field, which we do to an astonishing and you might say ludicrous degree. We have to characterize the optics extraordinarily well just to be able to remove the star field to the degree we have. Ritesh Patel, who's been focusing on how to do polarization analysis and also prepared much of today's demonstrations. Derek Lamb, who has done a lot of the analysis behind the calibration and other aspects of the SOC, and of course Dan Seaton, who's helped oversee the process as well. I want to thank the tireless operations team. That's Jillian Redfern, Zach Weens, Zach Talpas, Sam Jones, and our PSE, Will Wells, who have kept this constellation in tip-top shape over the course of over a year of operation in space. And that is just wonderful to see. And of course, gratitude to our relentless science leadership. That's Sarah Gibson, who kicked us off, project scientist, who has shown extraordinary patience and diligence in herding the cats and getting us all on track and keeping us that way. And of course, all of our working group leads who are named below. Thank you to everybody for this incredible milestone of this movie. There are those who doubted that this would ever happen. I never did, but just viscerally, it's very different to see the transition to the solar wind in this manner than it is to anticipate seeing it that way. So I hope you'll join me in thanking these folks. With that, back over to Sarah.
Yeah, let's actually take some questions. I see Sam had a question about the Parker spiral, and yeah, I think it's one of that's what I think we're looking at, and it becomes clearer with every iteration. I don't know if others want to comment on it. You know, we're not looking down from the top, the traditional Parker spiral, but with the projection, you still expect to see spiral-like structures in the simulations like the Gamma one that Craig showed at the beginning. You see that kind of spiral structure towards the poles, especially in projection. Yeah, anybody else? So that means, and that is here, I believe, Kurt, stream interaction regions, right, is what we're looking at. Where's Kurt?
Here.
Yeah. Okay, Craig, why don't you take the questions in the chat? There's another one.
Oh, I'm sorry. Okay, looking in the chat now. Let's see. I see Sam Badman. Incredible. Is the clockwise bending of some of the bright streamers toward the outer edges of the field of view, the Parker spiral starting to form? I'm not sure. I will hand that off to Kurt.
Well, actually, that's what I was just answering.
Oh, yeah.
Sorry, I meant the question after that.
Forward modeling, that's so exciting. Does this movie use NIFI data as well? I use the inner limit of the field of view 6RS. Oh, I glossed over that, and I'm sorry about that. We still are not incorporating the NIFI data into the mosaics. They're not quite ready yet. NIFI has a lot of stray light induced by the Earth, and that's been overwhelming to the images. So what we have done for K, and the reason it looks different than the J data, is we now are cropping the Wi-Fi data closer to the sun. You may remember, some people will remember, when we commissioned Wi-Fi, it turned out its stray light performance was so good, we were able to operate closer to the sun than the nominal position. It's supposed to pick up at about 20 solar radii, but we're actually pointing the Wi-Fi's almost 2 full degrees closer to the sun. So the inner limit of their field of view is 12 solar radii. And we're cropping a little bit outside that just to avoid edge effects. But the current mosaics, which are Wi-Fi only, begin at 15 solar radii. So that's well inside the LASCO field of view. We will incorporate NIFI post facto once we get the stray light under control, and there is major progress on that front. It's just not far enough yet to roll into the mosaics.
And there's another question from Yami, actually to Kurt and Sam about the spiral structure. Could it be a perturbation of the CME? What do you guys think?
I don't think so. I mean, I'm seeing it often enough, even in the eye data with the processing that I've done, that it's there a lot of the time, most of the time, and not when CMEs are present. So it's not just perturbations from a CME. It's definitely something else, something more permanent.
When we forward modeled the gamma simulation, we got it, and there was a CME there, but there was only one. It wasn't as complicated. So yeah, I agree. I think we're looking at a projection. What do you, Bernie? Do you want to comment?
Yeah, we see the co-rotating structure all the time, and it's there. And yeah, if you want to, now you're going to have a problem because you don't know whether that intermittent structure in the CME is in the co-rotating structure is a CME or not. And that will be a problem because you'll have to make a definition of what you're trying to do, or not worry about it like I have for about 20 years. Sorry. And because you surely see big structure in the co-rotating features that are segmented.
And when you say you see it, you mean in the IPS or in the SME, or in what data do you mean?
All of the tomography and the analysis that we've done from the Helio spacecraft on up. We have several papers on watching those structures.
I will say I've been looking at these movies, and the sheer kind of continuous nature of CMEs just spitting out constantly. I'm looking forward to solar minimum to answer a few questions. But it's super exciting now.
Yeah, it's nice to see.
Let's see, did we get everybody in the chat? Does anybody else have any questions for Craig right now? If not, let's hand it over to Chris. And Chris, why don't you go ahead and load up? We've noticed that it takes almost a minute for the things to come into focus.
Next one's good.
Perfect.
Yeah.
You're all good. Oh, it's Marcus. I'm sorry,
Yeah, I
Marcus.
thought it was next. Sorry.
You are. I'm sorry.
Let me just switch over here, and then is it coming into focus?
Yes.
You actually started in focus, so I don't know what it is. But
It's just my computer likes to do that. I'm going to move this down so I won't be able to see the chat, but you'll be able to see everything. Okay, so I'm Marcus Hughes. I'm the Punch SOC lead, and I'm going to give you some updates about the data. So I want to start. I've shown this slide several times, but I just want to have two purposes for it. One is to remind you that these smiling faces are here to help you with your data. And second, as Craig was mentioning, the SOC and all of the Punch team have put in a ton of countless hours, weekends and late nights to try to get to this data release. So I want to thank all of the people with pictures here, and also I wanted to mention Matt West, Joe Plowman, and Sarah Kovac, who have also contributed to the SOC and just aren't active members at the moment. So if you see any of us, please ask for help if you have problems with the data, and we are happy to show you some new results. So Craig showed this movie, and I'm going to show it again, a little bigger maybe, and tell you a little bit more about it. So the movie on the right is this CAM product, the level 3 CAM product for version 0K. It's available now. The data in this movie is available on the SDAC. We don't have a ton of extra data at the moment because it's a very iterative process. Like getting to a release takes a lot of development. And then whenever we start to release, we have to build up a long baseline of new products. So this is a limited sample of September 2025 data, and that's available on the SDAC. And I just wanted to give this concept of the scale we have here, because this movie required the generation of about 500,000 images, which is a lot of images to go into like a 13-second movie, I think is what it is. It doesn't have the polarized data here, so this is just the clear kind of total brightness image. And we are validating the polarized images so that way we can make sure that some of the changes we made are consistent and improve the data quality before we release them. But here you see the moon dashing across, coming out the left side now. And as we talked about, there's a lot of structure that's just flowing out. And I'll zoom in on some of it in a little bit to show you some more details about it. So let's talk about some of the improvements and then some of the things that we need you to be aware of about version K. First, we checked the nonlinearity and have fixed the offset in the earlier processing of the data, so that way it's more correctly handled. So that makes a small impact, but every small impact adds up to this glorious movie that we're showing. We reduced the cropping. So here you can see from between version J and K, the triangle in the middle gets much smaller. So we actually had all the data, but we were cropping it because we were having troubles processing it, but we've improved our processing approach. So that way we can go all the way down to this smaller triangle. And so you can see that before there was a whole structure that was hidden by our crop. So it's exciting that we can give you more of the images that we're acquiring. We've been working on making sure that problematic detector regions or problematic parts of the images are masked better. So here you can see that there's a saturation spike that shows up in this J image that's gone in the K. And so other kind of processing like that will make it a little less flickery in the movie. A big thing that happened is we have a new approach to stray light modeling that solved some bugs that I'll show you in version J, and just made the images much more seamless and much easier to analyze. As I said, we haven't released the polarization for version K yet, but I think we fixed the problem that we discovered that should help make it more correct. And then we've turned on star subtraction. So the products on the right here don't show the star subtraction. But if I flip, I think, to the next slide, you can see the scale of all the background removal that we're doing. So left is a version J image. So that's what we were releasing as CAM at that point, the CAM product. And you can see just the sheer number of stars in the image. And I've then scaled to the same scale, the right image for version K. And the stars are greatly reduced. In addition to the stars being reduced, you can see that the F corona, so there was a bit of residual kind of F corona here that's been removed better. And we're just left, I've saturated it so far that you can't see all the fine structure, but the fine structure is in there in these images. And another thing to point out is that there's some kind of stray light over here on the left in the version J image that's now gone in the version K. So we're handling a lot of the background removal in a much better way, so that way we can make more science-ready products. I'm always blown away by the number of stars that are in a Wi-Fi field of view. It's astonishing. To show you a little more context for the improvements we've made, so this is a movie showing version G, H, I, then bottom is J and K. And so when we start, you see that there's some kind of weird, like, it's going away now in the version J images, but there was a spirograph kind of pattern that we didn't anticipate in our original calibration. So we released data that had some spirograph pattern, unfortunately, but that's gone in K again. So we fixed that regression between version I and J. You'll see right now G and I don't have data. That's because we haven't processed all of the back catalog for every version. It takes a lot of time. So when we switch between versions, we kind of clean the slate and then start processing again. And sometimes we don't get all the way back through the data before we release the next version. So here it is playing again. You can see all that residual spirograph kind of pattern that I was mentioning in the J image that's gone in the K. And the K image, it's almost silly to put the Wi-Fi labels because it's so much cleaner that you don't even know that you have 3 imagers spinning around there to take the images. So now I want to talk about some known challenges that are in the data. So I've taken the zoom in of this movie, and I haven't, whenever I made this zoom in, I just used iMovie. I didn't actually rescale. So there's more detail that could be revealed of this if you just cropped in the actual data instead of cropping in an existing movie like I've done here. But there are residuals, if you look closely, where the stars have been removed. We think that there's a fixed offset that's happening whenever we're subtracting the stars, because you'll notice that all the little stars have like a little black dot to the right-hand side of the star core. So I think we just have a slight offset, probably like an off by one kind of error that we need to correct in the star removal. If you look closely, there's kind of a shimmering, almost like a grid pattern. It's not very prominent here. I think we fixed most of it, but in our early preparations for K, we were noticing it in the inner part of the field of view, but I think it's mostly gone. And then the other thing I'll note is that there are some bad frames that are making it into the mosaic. So if you watch, there's flickering, like right over here on the left-hand side. Occasionally you'll see a very bright frame appear. And so we're gonna work for the next version to make sure that most of that, the bad frames are removed so that way the mosaics are less flickery. But even with them there, I wanna point out that in this zoom in, and I'll have another one in a bit, but you're seeing structures like go pretty far out into the field of view without doing any kind of fancy scaling or post-processing. So we've definitely revealed much more of the signal that we're trying to observe and removed a lot more of the background. So what's coming in the next version? There's a lot of things that we're working on right now. Some things are actually almost ready, but we just wanted to hold off before pushing everything into one version. One thing that we've realized we need to do is we need to have some better image alignment again. That fixed offset needs to be fixed, as I mentioned. We have improved the point spread function handling, so that way it'll include a correction due to the pointing jitter. So whenever the image is acquiring, there's a little bit of jitter of the spacecraft, and that causes the PSF to smear from image to image. So we're correcting now, we're gonna correct for each image, make an independent point spread function update, so that way our stars can be removed even more seamlessly. We're gonna work to make fewer residuals in the star field subtraction because of that, these two improvements that I just mentioned. Another big thing that we're thinking about is trying to speed up some of the algorithms. We've paid attention to that some as we've been going, but there are definitely some places where we can optimize so that way we can release data even quicker. Right now, it takes a while to get through that 500,000 images for the 13-second movie. And if we can just have small savings here and there, it'll get us much closer to a full catalog at release. We're going to work on making accurate wind tracking products. So we've been internally looking at generating the wind speed tracking product as part of version K. We haven't released it, and we may not release it because it has some known challenges that we're working with Raphael about. But for the next version, we'll work on releasing wind speed tracking that is ready to be used instead of just a preliminary calibration product. As I mentioned, we'll work on the improved rejection of the problematic frames. And then our plan is that we'll release a new version of data in advance of the Punch 7 meeting. It'll have most of these things, I think, but we'll let you know whenever we're releasing the full details of what the changes are. But in the meantime, we're going to work on having the pipeline just generate a more complete V0K catalog. So instead of just the September data that we have right now, we're going to try to fill in a lot more events. So that way you can analyze a wider set of scenarios. So I'm going to switch gears a little bit for the moment to talk about how you can interact more with the Punch sock. So we've talked about the data, and now we want you to tell us more and interact with us so that we can continue to improve the data. So if you go to this URL, github.com, punch mission, punch bowl, you may have to sign in on GitHub, especially to interact. I think you have to sign in. But there are a few things I want to point out. First, there's this issues button. So you can always go to this issues button and see if we're already tracking something that we need to work on. And if not, you can open an issue and say, hey, I think there's a problem in the data or it's a problem in our code or something, and let us know so that way we can continue to improve the data. If you have a question that isn't particularly an issue, maybe you want to know, is there a way I can do this analysis? Or is this data available? Or what's just any kind of question, you can go to the discussions button and open a discussion. And I'd like to see a lot more discussions so that way the entire community can be aware of everything that's happening. And then finally, we'll look through this a little more. There's the SOC documentation website where we describe the things about the versions of the data and the product codes and have some examples of code usage. So if you clicked that button, it would redirect you to punchbowl.readthedocs.io. And this is what you would see immediately. I encourage you to go through these first few bullets. So go to the introduction tab, or you can just click here, and it'll describe to you a little bit about Punch and about the Punchbowl code. And when you're ready, you can then start to get data, and by clicking on Get Data or clicking on Data to learn more about the data products. You can check out the Examples tab to see some more examples. We also have some documentation about every segment of the pipeline analysis or the pipeline calibration. Some of it has become out of date, so we're working to update that. But there's a summary about what we're doing in each step. It just needs some updating. And if you're like a power user, you can go, a Python power user, you can go look at the full API for all of our code calls and see everything fully documented. So that's hidden either in, you can click on full API or go under more and see it. So we've talked about these level 3 CAM products, and I just want to summarize that the level 3 is the last level of processing. So it's the highly processed data. CA means clear A grade. So it's like the best quality data we're making in the clear filter. And then M stands for mosaic. So right now, L3 CAM is what is available for version 0K. Once we release L3 PAM, L3 PAM, I think that'll probably be your go-to. So what it includes is the total brightness image and the polarized brightness. And so it'll be the most useful because you can quickly get your hands on both the polarized and the total brightness. If you want a full list of the product codes, it's available in the Punchbowl documentation. So if you go back to that website, click on data, there's a tab that tells you all the codes, and it looks like this. It's much longer than this. We make a lot of products. But the things to keep an eye on are these level 3 fully processed products. And right now, the CAM product is the one that's available. And before too long, we'll have the PAM product available. That'll probably be your go-to after that. I've also mentioned, we've been talking about these data versions and the iterations, but I didn't define what we mean by a version. So a data version is just a number followed by a letter. So 0A was the first version, and then we followed that by 0B shortly after. We're now at version 0K. At version 1A, the data will be considered nominally calibrated. So they'll be much more stable than we've been doing right now. We've been making lots of big changes, but at version 1A, we'll be much more content and be releasing fewer versions after that. The data version history is documented in the Read the Docs. Unfortunately, I didn't get a chance before this meeting to put in the 0K notes. But as we've been approaching the more stable version and knowing more people are using the data, we've been trying to put more details into these data version notes, so that way you can understand what happens between each version in more detail and know when you need to switch for your scientific application. And finally, in the documentation website, there's an examples button that says, has some examples of how to use the data. So if you want to know how to plot it or animate it, these are all using Python. But you can do the same thing in any language that you like, because we're writing our files in FITs, so they're transportable and should be usable in any language. I will note that we probably should put this in bold, but if you're using Python, you should start with this environment setup example to actually set up the environment that's required to run the rest of these notebooks. But if you're not running them, you can click on them and just see what's happening in each of them. So this is my last slide, and I just want to remind you that version 0K data is, the September data is available for level 3 CAM. And the future dates and products will populate in the coming weeks. This next version of data, I think, will have even more improvements, but this version 0K is available and ready for scientific exploration already. You're going to hear from some of the SOC members right after this about how to get the data actually, and then an example of how to analyze it for CME tracking. And finally, as I said earlier, if you have feedback or questions or comments, feel free to go to the GitHub. We encourage you to go to the GitHub first because it's a more open platform, and we're all about open science with Punch. If you have a question that's more one-on-one, you can always email us at punch_soc@spirit.org. And then the last thing before I end is this is a zoomed in movie. Once again, I didn't actually resample the data, so it's kind of a zoomed in of an existing movie and is a little blurrier than actually is possible with Punch data. But here you can see Comet Swan in the middle. If you wait for it, you can see the wiggling of the tail right at the end. So there's a lot of exciting possibilities with the Punch data and Punch science, from the intended primary goals of helioscience, but also comet exploration and stellar exploration and lots of other things that can be done. So I encourage you to start using version 0K as soon as you can. And that's all. Thank you.
Thank you, Marcus. Beautiful data. Okay, so we had a little discussion in the chat about how clear and total brightness are essentially the same thing. But total brightness, the reason PAM is your go-to, part of it is that you get the 4-minute cadence along with the polarized brightness. So it's a good one. You can just kind of get it all. I think you'll hear more about the data format. The PAM files are in a FITS file with multiple extensions. And so there's various ways you can access that. We'll talk about that more later. Other questions for Marcus right now? Okay, go ahead, Bernie.
Just a comment in the chat, that's all.
Yes, your comment that you can show us how well you have characterized the F corona in different versions. Is that something you wanted to talk about today or just in future?
No, I can do that in the future, maybe tomorrow.
Okay.
Yeah, that'd be cool to see how we're doing with the F corona removal. For people interested in stars and comets, is there an optimized data level more than level 0 that doesn't have star subtraction? So we haven't released it for version K, but the CTM product, the level 3 CTM product, has the stars removed, but the CIM product does not. So we should outline in more detail which products have the stars removed. Maybe we should make a table in our documentation about, or some more hints of where to go directly, because the helioscientists might want PAM, but the comet and star people will probably want PIM or CIM instead. And
Marcus, the F corona that you take out is available as its own product, the thing you remove. And I think there's some intention to make the star field also a product that could be a standard.
So we save the F corona as a separate product, and we save the star field as a separate product, so that way you could add them back in if you wanted, or you could just look at just the product.
We have another question there from Pratam.
Yeah, so there is a little black splotch that moves from the left to the right in the image in the movie. And it is a processing artifact. So when we built the starfield model, we didn't use a long enough baseline of data. And since we have a hole in the middle of the WIFIs, there was missing data. And so the starfield model has a similar small weird shaped hole. And so when we subtracted it off, it left an artifact that moves with the stars. And so that's another thing that I should have pointed out. We'd like to improve for the next version. I think it's as simple maybe as using a different range of data when building the starfield model. So.
Excellent. All right, let's go on to Chris. And again, we're going to have lots of time at the end to ask questions and so on. So Chris, why don't you go ahead and load up your, and I'll give you a thumbs up.
Sharing here.
Yeah.
Okay. And while that is loading, I'm going to drop a link into the chat. Okay. So this is going to be a collab version of the notebook that I'm going to talk about today. So feel free to take a look at that. I think you make a copy of it, execute it, etc. The only difference between that and the notebook that I'll run today is this little bit up at the top that will actually do things like install Punchbowl and all the other tools. It'll also warn you that you'll need to restart the notebook if you're following along with this. Okay, so with that, I'm going to swap over to this local version of the notebook. Let me know if that is clear now or if it's not clear.
It is looking pretty clear. Yes.
Okay, perfect. Okay, so I wanted to talk about how to get access to the punch data and then how to do some basic visualization with the punch data. And so this is just a simple notebook that will go through a couple steps in that process. So the first little bit up at the top, all you have to do is import just a very minimal set of libraries. If you install Punchbowl, like another Colab notebook, it will install all the other dependencies like SunPy, etc. By the way, if you have any questions about getting a Python environment set up, feel free to reach out and we're happy to help troubleshoot that. So again, up at the top, we're just doing things like importing sunpy.net, their Fido tool, which is very useful for querying and then grabbing data from the VSO. And then sunpy.net attributes, that helps you filter out data in your Fido search query. There's a bit here where we import Punchbowl as a whole. That does some magic with sort of modifying Fido a little bit so that we can do some custom searches for punch data in particular. And then I've also imported two basic libraries from punchbowl.data. One is punch_io. We're not going to use that in today's example, but if you do want to actually load data from a FITS file to an IndyCube object, that then you can access the data, you can access the WCS, you can access all the metadata, all the uncertainties. You can load that with the punch.io.load IndyCube from FITS function, but we won't be using that in today's example. There's also the visualize package, which that will let you plot the data, you can animate the data, you can load the color map. All those tools are contained within visualize. Okay, so with that, I wanted to start off by querying some data from Fido. Here we're using a very cool tool that Sam Van Kooten put together where we can dig down a lot more with granularity in terms of querying the data. So what I'm doing here is building a search using Fido, and I want to store the results of that into this result cam function, or variable rather. So I'm giving it a time range. In the notebook on Colab, it's a much more restricted range, but here I'm doing, I think, all the V0K that we had made as of last night. So from September 14th until about October 3rd. I'm then specifying that I want a.punch.product code of CA. So again, CA is the clear A grade mosaic part of that CAM code. And then I'm saying a.instrument.m. So m is for the mosaic here. I'm saying a.level3 for level 3 data products. And then I'm specifying the data version to be the newest. You can also change that from some of the notes over here. And then I'm finally specifying that I'd like FITS files. And I'll talk about it in a second about how to change that last parameter. So say you do want to run this. I'm going to go ahead and execute the cell. It's going to run through and try to grab all of the CAM data products over that entire time range. There's one little bit of extra code here that I put into the notebook just to make sure that we're filtering out only V0K data. And so this will chug away for a second or two. And then eventually it will print out a table with all of your resulting data products. Okay, so this will specify every row here is a separate data file. You have the timestamp for it, the level, the product code, the instrument. You can see we build that, again, CAM product from those two codes. The data version is V0K. This is punch data, obviously. The provider is Swery, and the file type is FITS. So you can also see that we've gotten back 494 CAM files. So let's say we want to modify that. Let's say we want to get PAM files instead. So what I've done is I've made a similar query over a much smaller time range now, just 12 hours. But here I've changed the product code to be .PA. So for the polarized A-grade mosaic in the PAM data code. Everything else has remained the same. The instrument is M for mosaic. The level is 3. The data version is the newest. And the file type is FITS. And I'm going to execute that. and that will give me back a list of PAM files. Now you will notice that this is returning V0J at the moment because we haven't quite turned on or released the PAM V0K data yet, but once it is available, you'll be able to do the same thing with the polarized data. One note that I think was going on in the chat as well about which data product you might want to use. Again, PAM and CAM are at the same cadence. CAM is clear data, PAM is polarized data. It's making a total brightness out of the individual polarized layers from the earlier observations, but more data goes into the PAM data product for the low noise version, so it will be able to be reduced down a little bit further and cleaner. Okay, now one other thing I want to do is change this to now query quick look data. So I'm again taking a look at the same time range. I've turned this back to CA for CAM. Instrument still M, level is 3, version is newest. But here I've changed something. I've changed down at the very bottom for the file type. Instead of a FITS file, I want to load a JP2 file or a JPEG 2000 file. So I'm going to execute this cell, and these will come back. Again, you can see these are V0J at the moment, but we're going to correct that so it gets V0K. But now the file type has changed to a JPEG 2000 file. So these are quick look products that we're making that are not, they're much smaller than a FITS file. They're pre-scaled, and they have the greater advantage that you can drag and drop them into JHelio Viewer, which Sarah Gibson will talk about a little bit later. There you can do all kinds of neat things like intercompare with other instruments, output movies in sort of a more GUI-like form. So it's a great tool. Okay, so how do you actually get these data? All I've been doing so far is making a variable that contains sort of a list of all the files that we queried from the SDAC. So to get the files, all you have to do is take that results page. So here I took result_cam, which was the search for cam data. And I can just say fido.fetch that result. And I'm going to execute that cell, and it will download them. Now, if you are downloading them for the first time, it might take a while. I've already pre-downloaded these, so these will, it's just validating it. By default, it's going to download these files to, under your home directory, there should be a SunBy directory. Under there is a data directory, and then this is where it will store all of the files that you've downloaded from that. You can see I even have some V0A files that I've downloaded in the past. Okay, that's still going to go along. You can also specify a particular output directory that you'd like to write the files to if you want to store them somewhere in particular and not just in that SunPy directory. The way you can sort of get access to that is if you hover, this might not work in Colab, but if you hover over the function itself here, fetch, it will show you all the options in sort of the doc string. So here you can see there's the path you're writing out to, how many connections it will try to establish, etc. Okay. And like all live demos, it will take a little bit longer than you might imagine to run in real time. So we'll give that a second to finish up. Okay, so now what we've done is we've taken all these files, they've all downloaded to that download folder, and now the variable files here is going to contain the actual paths to all the individual files. So actually, I'm just going to do this live. I'm going to put a new thing here. I'm going to print out files, and you can see it's just pointing towards every file that it's downloaded onto my local machine. So now we can visualize this. So I'm going to take our visualize library that we imported earlier, and I'm going to say visualize.plot punch. And this is sort of our bespoke punch plotter that will use a lot of sort of best parameters to plot this data. And here what I'm going to do is I'm going to take the 250th file that I downloaded, and I'm going to pass that just location into plot punch. And plot punch is going to do all the rest. It's going to load the data from the FITS file, and then it's going to plot that on screen. So I will run that. Okay, and there we have the data. From there, you can do, you'll notice by default, it does a lot of things. It plots a grid, it plots axes for the helioprojective latitude and longitude, it plots a color bar, it plots some informative information up at the top about the product code and the timing and all that. But we can change that. We can scroll down, and let's say I want to make a prettier version of the plot, say to throw into a presentation where I don't really care about the axes or the color bar or all that. I can specify in the same plot punch function, I can specify axes off is equal to true, And if I run that, it will take away all the axes, take away the color bar, and just plot the data itself, along with a little bit of information down the bottom left, just the product code and the timing information. We conveniently have a nice little gap in the data to put some metadata. So you can also get a lot more complicated with it. Here I'm doing the same thing, but I'm taking the 250s file, but let's say I want to change some of the parameters. I want to change the Vmin, say, to 1e negative 14. I want to change the Vmax to 5e to the negative 13. Let's say I want to change the gamma value. So instead of 2.2, I want to use a gamma value of 3 in this case. Let's say I want to change the axes label from helioprojective latitude longitude to this X image and Y image. Let's say I want to change the grid spacing to 10 degrees instead of 15 degrees. And let's say that instead of punch cam, I'm going to label it as a punch clear low noise mosaic. So I can specify that with title prefix. So I'm going to execute this cell. And there we go. So you can see it's a little bit brighter than the data from before. We've changed the top end of the scale a little bit. It's now, instead of cam, saying it's a clear low noise mosaic. And the grid is brought in a little bit finer as well. You can also turn the grid off as well. So all of that, you can change all that however you want. There are a lot of options in the plotter itself. Again, you can hover over it in some instances and it might show you. In this case, of course, it's not. But if I scroll over and go to GitHub, I'll just drop this in the chat. This is the actual visualize.py file that contains the plotter and the animator. You can see that we have a lot of different options for the plotter itself, along with some default values. So there are all these values within here, as well as some documentation describing what each of these parameters does as well. So now let's say we want to animate this data. We can go down here and we can just say visualize.animatepunch. And now, instead of giving it one file, I'm going to give it all of the files that we downloaded. I'm going to specify an output path, which is going to be just on my desktop. And then the animator will pass through a lot of options to the plotter itself. So the same options that you could use while you were, say, trialing, building a version that you want to animate, you can pass those same options through to the animator down here. So here I've said axes off is equal to true. And then I've also invoked this option called trim edge, which is going to just do a little bit of cropping at the inner and outer field of view, just to make it a little bit less jaggedy in some places. And then I've also set FPS to make it 30 frames per second. So I'm going to execute that cell. And do be careful with what machine you run this on. By default, it will use all of the CPU threads that you have on your computer. So it'll just spawn off lots of individual plotters. They'll go off and render all the individual frames to a temporary directory, and then it will animate them all into one movie in the end. So that's going to run. It'll just take a second here. Progress bar always seems to move glacially when I'm actually staring at it.
One thing to note, right, Chris, is that this requires FFmpeg to be installed for the animation.
Yes, it does. That is actually a very good point. So that can be installed with something like Homebrew if you're on a Mac, or I think maybe Conda can actually maybe install FFmpeg for you as well.
Yeah.
But again, if you have any questions about how to get that installed, please reach out to us and we're happy to help. Okay, that finished up in just a minute. And then if I go over here onto my desktop, there's now a punchcam.mp4. I can open that up and I can play that. And this was, again, all of the V0K data that we had as of last night with the default scaling that has now been updated for the new data. But again, you can just see, I think I watched this for about like half an hour yesterday, just staring at it. Okay, and that was everything I had about that. Like I said, that Colab notebook that I posted in the chat contains a lot of the same things that are in this live notebook here. And then we can also update our example gallery notebook to include some of the changes as well. That was everything from me. So please let me know if you have any questions. Happy to help with anything.
Michael has
Was there
a
a question?
Yeah.
Yeah. Hey, Chris. Yeah, this is awesome. I mean, great notebook. Really happy to see it. One thing that I do see Craig and other folks doing is overlaying data from other sources and
Yes.
a chronograph. Do you have example notebooks for doing that as well?
I've thought about doing that for a long time. So two things. One is you can do that easily in JHelio Viewer if you just want to sort of, and I think Sarah will show an example of that. But like that movie Craig showed earlier with the SEACOR data in the center, it made that by just taking SEACOR data and reprojecting it into the mosaic field of view and then overlaying that on top of the data. So I don't have an example notebook, but that's a very good option that we could add into that to do it sort of in a notebook form. So thank you for the suggestion on that.
Yeah, thanks.
And we have a couple more questions. I think Chicho Pecora's question about the collab example showing brightness values, I'm pretty sure that's what you're going to do, right, Ritesh?
Something similar. Yeah, we'll do something.
Okay, so we'll get something, at least partially
Yeah.
answer that question there. And then there's Sam.
Sam was asking about minimum Python. I know I've been testing this with version 3.13. I don't know, that might be a Marcus question about what our minimum Python version is. I think for a while we were using 3.11, maybe as a minimum version.
Sorry, I lost my chat, but I think we actually have put in our project at TOML now that it is 3.13. But let me double check before I say that definitively.
I think our
Oh no,
CI
it's
is running
3.11.
3.
Sorry, we can work down
Okay.
to 3.11. So our CI is running. You're right, for 3.11
Yeah, I think we're running 3.11, 3.12, and 3.13 on the CI.
and 3.14 now.
And 3.13, yes,
The Pi version of Python.
exactly. But yeah, like I said, if you have any questions or if you have any suggestions on plotting options that might be of interest to you in particular, I know one thing that I was brainstorming this morning was adding a circular grid to really visualize in solar radii or angular distance out. But please contact us and let us know.
And I'll comment that we have the hour of office hours at the end. And if people want to try running this collab themselves on their own Python install or on the Go collab, please feel free. We'll be here to help troubleshoot that. We're not, at the moment, we're not walking you through like how to run the collab on the web, but you can do that without a Python install and we can help you with that. We have notes from the previous 2 sandbox where we did kind of plan for that. And Craig, did you want to make a comment before I go on? Oh, we have a question.
Oh, just because I was just going to leave in the chat, but since the images aren't a controlled projection, which is this azimuthal equidistant projection, the pixel location on the grid actually has physical meaning that you can extract fairly straightforwardly. So we have had studies, some of which are in the process of being published now, using rotoscoping tools, but rotoscoping markup tools can be helpful for that kind of thing. And that speaks vaguely to Michael's question, which was really about trajectories that are known in advance.
And Marcus, since it's open access GitHub, we also can encourage people to create notebooks themselves and add them to our notebooks. Is that correct, Marcus?
Yeah. So if you have questions about how to do that, we have some documentation on the punch poll. But if you have questions about contributing your own examples, we'd be happy to answer those because we would like as many examples as possible.
Yes. All right, cool. So Dave, why don't you start sharing your screen? Because the next section, we're going to talk about some CME tracking. And we're going to show, for example, what's called a JMAP. And we thought it would be good to have a introduction to that section so people know what we're talking about and why they're significant, why they're interesting. So Dave, are you here?
Yes, I have to figure out how to do this.
Yep. So you can go ahead and share. Meanwhile, folks can keep asking questions if they want.
Let's see.
So going back to Yara's question, Marcus is going to capture that, but in the short term, just epsilon cubed is a great filter to use because the coronal brightness falls off as epsilon to the -3 as when it's close to the sun. So it's a good one to start.
And that's a good foreshadowing of this upcoming discussion, right? Or is it related to this the mass buildup pattern power law that we were talking about?
Definitely that's intentional foreshadowing.
I figured it was. Dave, we see your screen, but we're seeing your Jupyter notebook. So see if you could share the
Okay.
PowerPoint with us.
Yeah, can you display it?
Sure. Oh,
might
you
be
sent
easier.
you did. You sent it to me. Give me 1 second. I will display it for sure. Hang on 1 sec. Okay. So tell me when this is, if you're, first of all, if you're seeing the right thing, let me go into display, and also if it's looking clear. Give me a second to go.
Okay, it's looking like it's there, yes.
And let me get this out of the way. All right. Does this look good?
Yes, thank you.
Sure. Oops. Sorry. Stop looking at now. There we go.
Okay, is that the biggest you can make it?
All right. How's that?
All right, so the idea here was just to give a brief introductory summary to producing what I call height time radius maps. They're kind of historically were called J maps in the past. And then Ratish is going to show a notebook, a collab on how to do this with punch data. At Boston College with Tom Kuhar, who I think is on the call, he's made some of these maps with punch data. So Sheely first published these kind of maps using SOHO data, LASCO chronograph data, so lower down in the corona. And then later on, of course, stereo data was used, the HI data. Down here in the left, we see Sheely's original, or one from the 2008 paper showing the tracks you get on elongation or angular degrees from the sun, elongation versus time plots. And then on the right, Davies and the UK people did this for HI images, also using the HI1 down at the bottom and the HI2 further out. And you can see all of the fine scale. They were very careful in how they subtracted out the background for these images. So next. At BC, we've made composite images by constructing 8 of the trefoils or mosaics, you get about 8 in 1 hour. A median is taken at each position to avoid spikes in the data. The image is tagged with the time of the last trefoil that's used, and the image is rebinned to 1024 by 1024. For the data I'm showing today, we've used just the version 0i brightness data. We tried 0j, but that's had problems. And we haven't looked at the K data yet. So we use difference images in constructing the height time maps. These data are summed by, again, elongation at a given position angle and radial width. Of course, you can use a width of a narrow width of a degree or so, but we have found that usually using a band of about 5 degrees, integrating over a band of about 5 degrees gives much better signal noise. So the result of this process is you get a brightness versus elongation. If the image is missing or otherwise has corrupted data, a blank line is inserted. The height time radius maps are constructed by stacking consecutive CME images along a given radius. For HIs like punch, it's best to use elongation versus time and use difference images and integrate over. You have to experiment with how wide the radial band you want to get the best signal noise. And of course, with the better data processing like K and the L3 data, that this should be no real problem. But for now, we've had to use wider bands to knock the noise down. And again, it's somewhat subjective which radio track you want to use to kind of define what the CME central axis or front is. This is historically a problem. Of course, you can take a whole bunch of radii if you want. And again, I think Ratish will be discussing this in a minute. So the outward propagating transients on these plots appear as inclined tracks. The geometrical shape of these tracks, the pattern, will depend on the propagation characteristics of the transients, in the sense that the shapes may indicate the acceleration of the CME, or if you assume a constant velocity of the CME, whether the front is tracking in the sky plane, which will be more like a straight line, or earthward, where it might be inclined upward, or behind the sky plane, where it might be downward. And these have also been used to track SIRs by Rouillard and others. And they can appear as converging tracks on high time plots, at least in the stereo data that was the case. Next. And so here's a, can you run that movie? The
Yep.
left, yeah. So here's our attempt using, again, version 0i data to produce the movie. This is the November 9th to 12th period, which is one of the key study intervals that we're working on now with the punch data. With this had like 3 CMEs going out, and on the right is the elongation time plot for this period. And again, it starts at about 8 degrees out for the eye data, I think. I mean, Marcus was saying now they go in even further, so that would be an improvement. But you can see the tracks moving outward from the sun pretty far out, almost to 40 degrees for that main one. And next, you can also use, by the way, a polar projection to get these, which I think Ratish will be talking about. So just finally, there's a punch field of view we've just produced recently showing the C3 image in the middle. We use C3, and of course, as Craig said, you can use C-Core, and hopefully eventually the NFI will fill in this gap completely down to 6 solar radii or so. And the idea is here, if you get the inner boundary, you can track the CME from near its onset time and what its acceleration profile might be. So that's it. Thanks. Any questions?
Thank you, Dave. And I see that this is the movie of the HALO CME
That's
from
the
November.
difference movie.
Yeah, from the November 9th one, right?
Yes.
Okay, from C3. Okay, cool. Any questions?
And we're working on embedding that move and making the full J-plot for this period soon.
All right, so let's pass it off to Ritesh. Thank you, Dave.
Thank you, Dave, for such a nice overview. Let me put my screen to share. Okay. Okay, my screen is visible. And let me put the link to the collab here. If anyone wants to run in real time with me, feel free to run in the background. And if you have any questions in between this presentation, just interrupt me. Don't be hesitant. So before I dive a little bit deeper in this particular notebook, let's see what CME we are talking about in this tutorial. So the data of version 0K that we have released a couple of days back focuses mainly in September 20th and around CMEs. So you can see there are continuous outflows, though when we picked up this CME, the one that's here, it's there, yeah. The one on 22nd, we didn't know that there were so many other interesting features, outflows, and other eruptions that were continuously flowing out. But for this demo, I have centered my downloading data set to the CME on 22nd. So the dates that you will find in the notebook are the September 22nd from last year. So coming back to the notebook, so I try to fill it very much with the text material, and as Dave was pointing out, so the main objective of this demo is to give you an idea about what we can do in terms of some science activities using the version 0K. And I assume that you have installed some of these notebooks, or not notebooks, but packages, Punchbowl, SunPy, AstroPy. But if not, and if you're running in Google Colab, you should be running this first cell, as Chris also pointed out. So first part of this discussion will be something what Chris has already shown, like installing some basic packages that will be helpful to read and visualize the punch data. Then this has been our routine from the first sandbox that we have done, is to mount a drive, Google Colab. I have already done that. So see, it shows me that it has already mounted the drive. But if you are doing in real time, you may need to do this to run these two cells first. But if you are running locally and you have already installed these packages, then you can directly come to this cell, the cell number 3, where we have imported all the useful packages that will be required for our analysis this session. The first 2 lines are actually, so let me start with the widget. So in order to do this analysis, there is some manual input required, for which the matplotlib display of widget is used. Those who are using notebook may be familiar with the inline version. That's the default version that notebook provides. But to be more interactive, to say zoom in, to click points, Matplotlib has this option of using widget, TK, or Qt. So there are different interaction features. But the beauty of widget is that it shows you the output within the cells, like after the cells. But the TK version, it pops up a separate window, and there you can do the same stuff. Some common libraries imported, NumPy, AstroPy, TuckDoom, as I call it, TQDM, is a very good progress bar feature, which worked till yesterday in Google Colab, but I tried it in the morning and somehow it didn't show, performance issues. And but it will run smoothly in your local environment. Some more Matplotlib and AstroPy imports. NDCube we have called because of that data format that we have been using within the Punchbowl. NDCube is like a bag of data, WCS and metadata, everything. And it becomes easier to transport between different cells. Some more scientific analysis based imports here. And this is the specific ones that Chris has already shown, that we will be using some imports to visualize it, input data. We also have a color map for punch. So if you want to have this golden kind of color map, or the copper color, I'm not colorblind, but I'm dumb with colors. So you can go to this CMap punch import within the Punchbowl visualize. And we have integrated from Raphael's notebook from last December, where he showed a demo of cross-correlation method to get the speed. So now it's available within the Punchbowl under level 3 as pre-processed image. So there are more functions, but this is the one that converts the image from the regular Cartesian to polar coordinates. So we have called this, and some additional widgets required. So developing on what Chris has already demonstrated earlier. So the time range here is from 22nd 9th, from around 3 to 9:59. So I have chosen a very broad window, you can see, from 22nd to 23rd. The time, just try to optimize it for the Google Colab presentation. And you can see here in the result that when the result is displayed, the latest 0K version is being grabbed. If anyone has any problem that it's grabbing 0J, please let us know. Technically, it should grab 0K, but there can be some other things if you have passed some other variable or missed something, then maybe you will get older version from directly VSO. So this is the first step where you just run FIDO search. I have already run in Google Colab. So this all list of data is loaded. And then I go to this step where we just download the data. And this is where that TQDM should show progress bar. But Google Colab, it has its own limitation and the data is downloaded. There is an alternate path that is provided here, that if you already have data downloaded to your local folder, say for me it was users, Patel, Sanpai, and data. That was my local path name. So you can just directly pass that path information in this cell and locally read the files. Don't need to download it every time, but since V0K is released recently, so it will be good if you can download it in the first time, and when you run it later, you can comment it out the other ones or directly run this cell. Just a quick sanity check about, so I'm just printing like what is the file name here. So the level 3 camp file, and for a particular time, it's V0K. So far, we have just revisited to brush up your memory, to reiterate what Chris has explained about downloading the data. Now, in step 2, once we have the data, as Dave was pointing out, that we can make elongation maps or the J maps or the stat plot, as we are calling out their different names. We can have different approaches, like one is within the Cartesian images, we provide, say, different sectors of fixed width along the radius. The other approach is convert everything to polar coordinates. Then it becomes easy in terms of everything being, say, rows and columns, which you will see shortly. So to demonstrate the Cartesian to polar, what we have done is we have loaded the ND cube from FITS. So this is a standard loader within the punch board. And this particular command returns the data, WCS, and metadata in a particular format. So if you are a regular FITS user and are using this instead of from fits.io kind of thing, like AstroPy version of data and header reading, so we recommend it to convert it into a FITS compatible format, which is this particular line here. And once this the input data's WCS and the metadata is passed to this function to FITS header, it returns the full header that's compatible with the FITS format. So here you see the display is in the usual format, but if I do just say, oops, not that thing, input data dot meta, it will return me something, but that's not easily interpretable in our terms. But if you do print and do the same stuff, it will return something that we are more familiar with. So this is just printing, but if you want to say, get one particular keyword, like say n-axis, date of time of observation or something, then either you can print it or you pass it to the full FITS format header where you can then access individual keywords. So you may be very much familiar with all the keywords here, but just a couple of ones that I want to focus here is the CR-pix and CDEL. So these are the center pixels of the Cartesian image. So we have 4K image, and this is the center pixels, which corresponds to 0.025 degree increment in X and Y direction. So that's just remember that this is in Cartesian. Now, coming back to what we were doing, to remapping from Cartesian to polar. So as I mentioned in the beginning, that we are going to use something from last sandbox that happened in December, and Raphael nicely showed all the conversion from Cartesian to polar, and then subsequently tracked the solar wind stuff. But here we will be just converting it to polar and then creating JMap. So the functions is already available in the punch bowl, and this is the same cell you can find in Raphael's older notebook with some very minute changes. And I have kept all the parameters same, so that if you revisit the old sandbox of ours, you will find it to be very much in flow with what we had earlier. So here the images are now converted to polar of the dimension roughly 2K by 3K, unlike 4K by 4K that we had. And remember when I told you to focus on a couple of parameters, which were C delta 1 and 2? It's not here. Here, yeah. So 0.025 degree per pixel was the pixel scale in the native format. And when we convert it into polar, in this particular example, the same has been retained. Like in the radial direction, it's 0.0225, but in the angular direction, the azimuthal direction, it has been changed. How does it look? Let me just show you one example. So this notebook is also live. Hopefully it doesn't crash. So this is just displaying that the frames, we are going from Cartesian to polar. Wow. Okay, it is showing. So the image on the left for this, oops, this shouldn't be happening. Okay. So the 0 in azimuth direction is the angle from solar north to counterclockwise all the way around. And the radial direction is from the center of the sun towards in every direction radially outwards at each azimuth. So when we say that the azimuth angle increases from 0 here to 270 here, so you see that at 270 we have a bright planet, and roughly around the same region, so this is, I assume it's 270, we have that same thing. So just to give you context that going from this to this, we are just deprojecting it. There is also a version of going from Cartesian to polar in SunPy reproject that you can also use to do this reprojection. But if not, if you are comfortable with this version, you can directly import from Punchbowl. And as Dave was pointing out, in their version of the eye data that they used, it was around 8 solar radii where it was masked, but now it has come down even below to around 5 degrees, not solar radii, 5 degrees. We are so used to using solar radii, right? So just moving forward, let me reiterate where our CME was. Coming back to this movie, the CME is located roughly at less than 270 and greater than 180 degrees. So somewhere around 240-ish position angle, right? So what we have done in the next step is use this code, the code that was to convert from Cartesian to polar, and extend it to the full time sequence. This is a kind of lengthy step, so I have already loaded the data. And there are 2 versions that we have put here. One is directly put the angular slice, and when we read the data and convert it into polar, so just make the distance time map of that angular sector that's defined here. Or the other version is we append all the polar images to one empty cube, and then based on our choice, we select which angles we want to track for the CMEs or any outflows. So this is the way generally Cactus and other tools operate, where we stack all the images as a 3D cube, and then at each position angle, we make the stack plot, height time plot, and then do the analysis. So far, any questions to anyone because things will get turbulent after this. I cannot see the chat, so if there is anything going on, please let me know.
There aren't any questions yet, Ritesh.
Okay, thanks, Marcus. Yep. So this is just the basic steps of loading stuff, and after creating a distance time map here, we see what's the shape here. So remember the y coordinate here we have given as 2000 pixels, which corresponds to 45 degrees. And on x-axis, the size is somewhere 2880, which corresponds to 360 degrees. And in the distance time stack plot, so there are columns of 58 images that are stacked next to each other. And the alternate that I was talking about, like if you have done already, say made a stack of all the images loaded in any method, like either use a load ND cube or use fits read image kind of thing, we just read, play or run this cell with a given angular range, which is in this example is 235 to 245, converted to pixels, so that we have appended only those columns and appended to this empty map of distance time map 2. One thing to notice here is that in order to create the stack plot here, we have used here nan median for this example, but you can also experiment with, say, nan sum or nan mean or any other version of your function of how to say average around or find the maxima in this 10 degrees pixel bin. So this 10 degree I have taken just randomly for now, but you can increase or decrease depending on what type of feature or what fine scale you want and how much signal to noise is required for a given structure to be tracked. So once we have run this cell, now is the main show time. So here what we are doing is doing some preliminary work of converting times to a particular format so that it's displayed accordingly. And the input image displayed is passed as input map. So this is just some kind of repetition done here. But the minimum and maximum, as Chris was pointing, some of the optimized values we have kept here, but you can also choose other methods like percentile or give your own numbers, your choice. Then the usual process follows: display the image with power normalization, choose some gamma and the range for that gamma. So for punch, we have found the gamma values close to 1.2, 1 by 2.2 or 1 by 3 works very well. And the same has been found for even these stack plots. After adding all these labels and titles, there is some additional thing done here. So this is to ensure that the x-axis, which is actually our time axis, that has the display in the UT format. And this is just the displaying of the image so that the vertical axis is degrees and horizontal axis is in time. And now there is a further section that you see reads like to store the clicked points. So we are trying to manually identify the ridges. So let me just plot it. And yep, this is the JMap or the stack plot that generates using the V0K. And for this particular CME, you see that it is very nicely visible, and perhaps it's extending beyond the time range that I have put in this notebook. So this is a very long-lasting CME, and we are reaching up to about 25 degrees elongation angle. So if you just vaguely convert it into the plane of sky, it's crossing more than 100 solar radii, and that's cool, right? With the new version, you can see these tracks, and there are many other features. You see that maybe other flows and other parts of the CME that will need some more deep dive. So coming to the next part here, what I was talking about is we draw the marks on the JMap So for this, there are some functions that we have defined here. And you can change all the symbols, like here it's just a circle with red color and the marker size. So this function, what it does is you click left onto the image, it will store the value. Like if I click it here, oops, so the red point appears, its value is stored in the memory, both the X and Y coordinates. X coordinate is saved as the UT time, and Y coordinate is saved as the elongation angle degree. So the instruction is also written at the top: left click, add, right click, delete the nearest. So if I have, say, accidentally clicked a point over here, and that will be a good outlier for your analysis. So just right click it and it's deleted. It's deleted from the arrays as well. So what we do is we can directly keep clicking wherever based on our judgment, where we find that, okay, it's the outermost part of the CME that we can think about. This is without processing. So this is just with Vmin and Vmax. We haven't come to any kind of radial filtering that Craig was talking about. So based on your opinion and judgment, you can put points, whichever feature you want to track. So I have put some points here, and once I am satisfied, okay, I have enough number of points. So there is a button at the top that says done selecting points. So when you click that, it will just show all the X and Y coordinates. It's a little messy, but you get the point. Like these two variables, the X coord dt and Y coord, has stored X and Y coordinates. Now it's up to you to whatever kind of analysis you want to do. You can directly perform with this. So in subsequent cells, I'm going to show just one or two basic analysis that we have tested, but it can be extended to further different stuff, manual or automatic. For this example, we have just shown manual one, but if you want to automate this process, you have the stack plots, and then you can do your own processing to detect these ridges automatically and get their kinematics information. So once we have got all these X and Y data points, we move to the next step, which is to convert the coordinates to speed estimates. The simplest idea that we can think about comes from our elementary school. When we have two distances, two times, we do just dx by dt, right? That's a very crude way of doing differentiation, and let me show you what the output of that kind of differentiation looks like. Oh, that's not so good. Maybe I have been so sloppy in clicking points, but it has been seen in many other previous studies as well. Like numerical differentiation always needs some care. There is one small point that I may have missed. So focus here, the speed is shown in kilometer per second, but so far we have been dealing in elongation angle. So either we can go with, say, angular speed, like angles per second or per hour kind of speed, or do some kind of approximation. Like for this particular example, what we have done is to converted the y coordinates that was in degrees to an approximation of impact distance on Thomson surface. So if you go to literature and find different papers like the one that I'm showing here, and look the standard picture of Thomson surface, which forms the sphere across the Sun-Earth line as diameter. So the impact distance is actually this distance d, which is sine of this elongation angle multiplied by the distance between the observer and the source. So this is just a crude approximation, but if you go to this series of paper by Howard D. Forrest and I think Tapin, yeah. So they have shown like its Thomson surface is not just a single surface, but it's a plateau and it's a wide range. So for the simplicity, for now, we have kept a simple approximation, but this is where the tweaking can be done to convert from angular coordinates to, say, the known kilometer coordinates. Coming back to this plot, this can definitely not be the the profile of CME propagation, that it accelerates and decelerates very often. That will be crazy, right? So you can apply some of the advanced numerical differentiation method, like by either smoothing the points, fitting, say, spline, or using some filter like Savitsky-Collet filter that takes certain points and fit the polynomial of order that's chosen here as 5, for example, or do some advanced regression method. Like for this example, there is localized Gaussian kernel weighted regression. Let's see how their results compare. So some description of it is given here. And if you want to know more, if you are not familiar, then there are many tools available, or the many videos available about explaining how these individual one works. The simplest is cubic spline that takes 3 points at a time and fits a curve around it. So that's the simplest approach, but there are better ways also to do regression instead of just fitting a straight line or fitting something crazy like this, just connecting the dots. So let's see what the results of this comes out to be. So in this particular example, even though I have clicked very choppy points, the best performance, which looks reasonable and acceptable, is the Gaussian regression, where we see that the speed remains almost constant or decreases slowly, which is kind of behavior of a CME that one would expect, that after reaching in the heliosphere, the speed remains more or less constant, or shows initial deceleration and then becomes constant. So this can be considered. The other fits that you can see is the Savitsky-Collet. So we're using the 5th order polynomial for fitting, still shows a lot of fluctuations, and the cubic spline was the worst performing among all 3. So these are not the all types of fittings that we can do. There are multiple regression methods that we can do based on the clicked points, and also it depends on the manual judgment. Like for me, these may be the points, but for you, the points can be somewhere further. Or as Marcus was trying to do, is zoom into the individual regions and then click on the points. But in automated methods, you can reduce those kind of biasness. So yes, there is a lot of judgment involved, but the goal of this demo was to show that we can make good height time plots and then do some preliminary science analysis as well. Now moving to the last bit that was also there in the chat, and Craig has foreshadowed about the radial filtering. So we are trying to examine the intensity evolution of this CME with distance as it propagates. So for this, there are a couple of functions written in this section that will help to again do something similar to clicking, but while plotting, this is the same cell as before, but here is the change. So if I go back to the earlier plotting, which is somewhere here, I may have briefly skipped it. So the input map was, oops. Okay, here. The input map was just the simple distance time map, but for this particular case, the input map has been scaled to the elongation angle. So here the radial elongation angle varies from 0 to 45 degrees. So that cube factor that Craig was talking about, because in the outer heliosphere, we have been taking this kind of normalization, and Bernie was telling that they have been using 2.3. So maybe we can talk detail about what is the exact number to be used. But for this example, let's focus that it's of the order 3. And when we do that, one thing is it will again show us a plot, and now you see the difference. So the radial gradient has been reduced considerably, and this structure is now visible more clearly as compared to the previous version of here, where the things closer to the sun are much brighter as compared to the farther away. So this kind of normalizes the intensity. So the function that I was talking in this section what it does is, like, if I click a point here, it doesn't just records the intensity at this point, but say if there is another point, so in the perpendicular direction to this line, it will take a box of 5 by 5 pixels and sum up the intensity. As the title of this section was to examine the intensity evolution along the curved path or the artificial slit that we are going to just place. So let's say we just track, say, very close to the leading edge, not going too far outer, because you see that there is a little bit of over subtraction or some, it may be a real feature of dimming kind of phenomena happening. So let's just put some click points here and hope this goes well. Once we are done, we select this button and 14 points are selected. Great. And it has been all like, so there are not just 500 points, but it is linearly interpolating all the values to between the 14 points that we have selected to keep it consistent. But if you want to change it, you can change the number of points in this line, where this function extracts the x and y coordinates and also the intensities. So here the thickness, the 5 pixels I was talking about, you can also change it to, say, 10 pixels or more or less, depending on how good SNR is there or how blurred features we want to study. So what now after that, we just plot like along those curved slit or the curved ridge. When we plot the intensity profile on the right, so what we see is it may be the real phenomena that it increases and then decreases. It can also be something that there is certain evacuation happening here. If it is real, then we are getting decrease in intensity, and since intensity is also related to density, so that's an indirect implication of this analysis. But yeah, just to give you a flavor about what we can do with this current version of data that we have. And though there are some artifacts still, but still we have some data to analyze signs like tracking the CMEs or the flows, or do this kind of relative analysis that the CME is initially gaining some weight and then it's slowly diluting as it propagates even further out. So yeah, that's all from my side. So you have this link of this notebook in the chat and also in the mail that Sarah and Marcus sent out. So you can try it out yourself with the same dates or some other dates, as the data will be flowing shortly of the new versions. Open to questions.
I see that there's a question from Pitandas in the, it says, for a typical height time map or an XT map, we usually take the average along the width of a chosen slit to improve signal to noise. What about the JMAP?
So JMAP is also, so height time map and JMAP all both derived from the same phenomena, as Dave was pointing in his presentation, that we take a, say, slice or say angular sector, and for the purpose of increasing signal to noise, we are, say, taking, say, 3 or 4 pixels or even more, binning them up to increase the signal to noise, and stacking them up with time. So for lower heights, like until C3 era, we had been mainly calling them height time map. But I think after heliospheric imager era, when the shape was more like a J shape, people started calling J maps. But
I think the question is just like, how big of a slit did you use? So a couple.
For this one, I had used 10 pixels wide because the binning is very fine. But you can test depending on how fine resolution of this map that you have made, the polar map. Typically, people use 1 to 2 degrees in angle, which corresponds to, depending on the pixel size, few tens of pixels in this case.
And Craig has a question. Craig, do you want to ask it? It's good to say it out loud too for the purpose of recording. I don't know how much of the chat goes with it.
Sure. The question is, Ritesh, have you yet tried Fourier filtering that stack plot to further reduce the vertical artifacts?
So far, no, Craig, but yes, that's a good point that there are these periodic features will be a good thing to remove with Fourier. Yep.
You and I
that.
might spend some quality time with these data later, but there's clearly some handles we can pull on, maybe even for the stock processing.
Yeah, good point.
So we have a comment. Okay. Wajesh, do you wanna make your own comment, or I'll read it? Either way.
Okay, I'm reading Vagish's comment. So in JMAP, intensity no longer strictly photometric, and there is artificial broadening of CME's fine features. So tracking at longer elongation may provide larger uncertainties. Do you agree? So yes, there will be uncertainty, and the overall goal will be to quantify those uncertainties. So this is very basic example that we have shown right now. And this kind of radial filtering is just to compensate for that radial gradient in intensity to normalize, so that in the same platform we can see that how things are with say further elongation angles. So we can have like improved uncertainty analysis on how these features move, and even in the same example we can find, say, at the very beginning there are fine features, but as we move along this JMAP the features get more smeared out. So yes, that's there in this data as well, but we can work on some more rigorous analysis techniques.
Craig, did you want to do your follow-up or comment?
Oh, sure. So Agish, punch measures radiance, which is a little different from intensity, right? That's radiance is an intrinsic quantity, so you average it over areas of the image rather than summing it. So I like to keep that nomenclature straight. But even these scaled images are photometric in the sense that there is a quantitative meaning to the brightness of each of those pixels. If you divide by the cube with the elongation angle, you get back to the original radiance that was being reported. As long as I've muscled my way onto the floor, banal, those vertical artifacts that we were mentioning, that's remnants of the fluctuations you're seeing in the K data. And they're prominent at the top of the image because of that R cube scaling. But I'm sorry, back to you, Ritesh.
Actually, Craig, Wageesh has another comment. Is it the case that pixel area varies with elongation in this? So Ritesh, or one of you guys.
Go ahead, Ritesh.
You can explain more, Craig.
Okay. Yeah, the pixel area is varying, and that's one reason to use elongation. To use radiance is that the radiance value doesn't change with the pixel size, whereas the intensity value, of course, would.
Yeah, because in the pipeline, we have taken the area into account while making the photometric conversion. So that's corrected in level 3 data.
And there was
Okay, thank you.
There was also a question from Dave Webb earlier who asked about error bars on the plotting intensities or speed.
Dave, so far I haven't put error bars, but like there can be multiple things like fitting error, measurement errors. Like for this stack plot, we have taken plus minus 5 pixels width. So the uncertainty within that 5 pixels can be a 1 sigma uncertainty in the intensity plot that we can do. Or so yes, that's one of the advancement that we can do next to keep error bars.
And then Craig, you want to answer Subhamai's question about the periodic pattern?
Okay. Yeah, we were talking about that earlier. That's the remnant of the rotating trefoil pattern that you still see in the K images. And it's very prominent in the outer part because of this R cubed scaling. But the fact that it's got such a great pattern in the time domain means that we have more leverage to pull on for future data processing.
All right. Are there any other questions right now?
Okay, I think Binal posted something.
I think Craig addressed
Oh.
Binal's question, pretty sure.
Oh, intensity is in MSB. Yes, that's right. Yeah.
Yeah.
So that's photometric calibrated. What is the reason of artifacts? Craig has answered that question because of some bad frames and some remnant artifacts that we still have. So that's why Craig suggested you go with Fourier.
Okay, so we're close to on schedule. I have one last part, which I'll show you, and it'll be fairly quick. And then we're going to be here for another hour to answer any questions you may have. And you can also use this time to go and play with the Python notebooks, to try your own things, and you can dip in and out of here. It's going to be an office hour, so people will still be here with this Google Meet until an hour, just over an hour from now. So feel free to do your own thing and then just jump back in and ask a question, but it's going to be quite informal. So what I'm going to do right now, though, is to just show you the really kind of quick and dirty, easy way to get the data, make a movie, but also to look at it with other observations. I am by no means a J-Helio viewer expert, which maybe is good because it kind of shows you how straightforward it is for somebody who just dives in blind and uses it. You do need to download J-HelioViewer. I have in the past used HelioViewer online, which is also great, but J-HelioViewer has a really nice thing, which is that you can drop your own files locally, which is useful with Punch. I will comment that our intention is to have Punch automatically uploadable to HelioViewer online and J-HelioViewer in the same way that you will see things like SDO, SOHO, Solar Orbiter are, but it's not quite ready for that. So this is how you can do it now, even before we are officially in the J-HelioViewer environment. So first, can you all see my screen, and is it non-blurry at this point?
Looks great.
Cool. I just wanted to point you back to the page that Marcus showed you with the introduction and the data, and you will see that there is a wget. So you can, even outside of a Python environment, just in a shell script or wherever, use wget to access files that live in certain directories. I also want to show you that you can go to the STAC. We have links from the Punch webpage to it, for example, and I believe we'll have links also from this page in the future. But this is for example, the CAM level 3 for that day. If you order it by last modified, that's the most useful because you'll notice it still has some J. It'll tell you what's there. And so this is a useful way to check and see if the latest data has made it there, because one point to keep in mind is that as we push these updates, they don't happen instantaneously. So at the moment, we've got data in the September timeframe, and it's slowly filling out in both directions. But it does take, I think, Marcus, maybe a few weeks before everything would be there. Is that right?
Yeah, it's going to take some time.
It's going to take some time. So you may have your favorite observation from November, and you want to know if the K data is there yet. And so you can just kind of go into a directory like this, and the answer is probably going to be no, but whatever, you can look, and you can see even when you do last modified, it's always level J. So that hasn't propagated, but it will get there. So be patient, it will come. There's a slightly different directory structure to find the JPEG 2000s, which I'm going to show you. The JPEG 2000s, for example, for September 22nd are there. And so again, use the last modified to see, because there's still some J sitting in there, but this all gets eventually cleaned up. But at the moment, this is where you want to look just to see if the data exists. So once you know the data exists, you can just run wget from your shell script. I made a little IDL code just because it's nice, kind of equivalent to some of the stuff that you were seeing earlier from Chris, that you can see, you just basically can change the version and the CAM, et cetera, and you can go to the JPEG directory or go to the FITS directory and download a whole day in one go. So I've already done that. And now I just want to show you, here's J-HelioViewer, which I have on my, I've downloaded. So let's see if I can get this to work. I tend to like to turn these things off and turn on the timestamp. And then really all you have to do is you take your JPEGs that are sitting here in my file in my laptop that I downloaded with a wget, and you literally, let's see if this works, you literally drag and drop. There we go, it takes a second. Sometimes if you don't see anything, so you kind of wait for it, try doing reset view, voila, and boom, you got a movie. It doesn't get easier than that. So just to show you that if you want to embed, say, other chronographs, you do need to change the date. So for example, I can look at this and say, well, this one started at about 00 and it goes to, it goes all the way to 2400. So I can just go up here and 2509, 2200. Maybe I have to do that. I don't know. P35900. Boom. And then I can go to new layer. I have noticed sometimes data accessibility comes in and out. So if you can't access it from, say, Goddard, try the Royal Observatory, or vice versa. Just try one of them. Let's try, let's actually go to SOHO. Let's get some LASCO in there. So we go SOHO, LASCO C3, and hit return.
Show me, first of all.
There you go. Oh, we've got a live mic, I think, somebody. And it'll take a second to load and it's probably gonna be a little slower than usual because I'm online with everybody. But in just a second, you're gonna see, I hope, the LASCO C3. And while it's doing that, just to point out that there are data from LASCO C2, there is data from SDO, so you can put in your AIA, Mauna Loa. By the way, I don't know if everybody heard, but Mauna Loa is open. The Mauna Loa Solar Observatory. We are back, baby. So there will be some ground-based data to support Punch and these other instruments very soon. Come on, it's going to take forever. Yay! I should have probably preloaded it, but I wanted to show you just how fast it was. Well, while it's doing that, why don't you, oh wait, let me show you something else in the meantime. While it's loading, I can actually go here and show you, you can do, for example, a running difference. Huzzah. You can do a base difference. Takes a second. Oh, I just made it unhappy. Ta-da. You can do a wow filter. Let's see if it'll let me do a wow filter. Oh, I just turned it off. So we're going to do, there you go. There's a wow filter with some radial gradients put in. It takes, it goes all glitchy at first, but and it may not allow me to, let me pause this and let me try one more time with LASCO. Give it a shot. Anyway.
Sarah, try other server.
Oh, I could try the other server. Yeah.
Goddard is.
Yeah, because Goddard can be tricky. Okay, so I will go, for some reason, Rob is not showing up. So I'm going to go with IAS. We'll go with SOHO. We'll go with LASCO C3. Yeah, definitely. I have found that you have to try different servers. There you go. Okay, cool. So we might as well throw in some C2 while we're at it. What the heck? We can hope that it's going to work, and then we can run a movie. And then we run the movie, and look, there's the CME that leaves there and goes out there. And here's a super fun thing to look at. You can change the projection to polar like this. Let me move this out of the way. Are you all seeing this, by the way?
Yeah, it's amazing.
Yeah.
Yep. So there you go. So here's the CME starting here, going out. I think that's the one y'all were tracking. And you can even do, and this is really nice, I've been looking at aspects data with Punch, log polar. So you can look at things compressed in the far field. And here comes that CME going through. So lots of fun things to play with in JHelier Viewer. And we will get our JPEG 2000s in there. I will say, if you should get the JPEGs in real time with the FITs, it is possible to do the same thing using FITs files. I could show anybody who's interested. They can be a little tricky because you have to actually change the levels if you're using the Punch dropped in the way I just did. So it's just easier to use the JPEG 2000s. If you're using PAM data, the FITs files have extensions, so it has both polarized brightness and total brightness. So you need to flatten them to a two-dimensional thing before you can drop one of those FITs files into JHelier Viewer. But again, the JPEG 2000s lets you do it without any fiddles. Okay, any questions? Bernie.
Yes, you're really well versed in what data are available currently, and I'm real interested in what's available. We've been using iData that don't have stars removed, I believe. And we of course deal with all of this, but we can certainly do much better with better data sets. Now, I expect the eye data are available, at least for brightness, and right now for most of the period October to November 2025. So that's okay. That's a good practice data set. What data have stars removed currently, and what are they called?
So that will be the version 0K. It'll be the level 3 CAM product. And at the moment, it's only available for some periods in September, but we are working hard to get a filled catalog so that way you can get, yes, this October to November and December, and even the recent data. That'd be nice. So we're working to fill in all the other dates, but right now it's just September. It's level 3 CAM.
CIM?
CAM. Yes.
CAM.
Yes.
Okay. Okay, first of all, what's J available? And that doesn't have stars removed.
Right. So we have a lot of J data that's has stars in it. There is a level 3 CAM product for J, but it has stars in it. We are working on making some kind of quick view dashboard so that way you can see where the data is covered, but that's not ready yet. So
yes, we're of course interested in the October to November data, and we've looked, and there's brightness at least for the J data with stars in it. So
yeah,
I believe.
Yeah, if it's available there, then you can use that CAM for J. But I will encourage you to, as soon as the K is available, please switch to it, because there are lots of problems on the J that I showed earlier. That
yes, CAM though is well, we've been just like I say, we've just been using eye data currently, and that works as long as we remove the stars and do this minimum map technique. We'll continue to do that since we don't like the flashy stuff that comes in every so often. That really gives a lot of noise to what we're doing.
okay.
And so we remove the stars as well as we can, and then remove the flashy stuff, and with the minimum map over an hour period, by the way, and then that allows a pretty clear view of those remaining pixels. We can continue for each pixel that we provide, which is a 1 degree size thing. Then what we can do is we keep since it's a minimum map from an hour period, we keep the actual time of the exact pixel that was used in the minimum and deal with that. So we get a good time for that feature in the tomography, no matter whether it's 1 pixel and the next pixel next to it has a different time within the hour. Anyway, it all works pretty well to remove any other things. We're interested in the zodiacal light that's present still, and we like to get it down as well as we can. And of course, the eye data have a lot of zodiacal light that hasn't been removed well. One question I have is the eye data, is the zodiacal light model that's been used continuous throughout the period, or do you have a different one that you've added in which data set?
So for the F-Corona zodiacal light model, we save that as a separate file, so you can go look at those. And the way we do it is we take one before the observation and one after the observation and interpolate whenever we subtract. So we try to make it as continuous and smooth as possible. But I will say that the version K, we completely changed how we were handling stray light, which greatly improved some of the F-Corona zodiacal light modeling. And so version K, as I showed in the slides earlier, has, I think, almost all the zodiacal light removed. But
well,
you
don't know what it is really right now, and that's the trouble. And I've got a way to find that out using the tomography analysis, because you get to the base. You have to figure out what the base values are in the analysis along each line of sight.
So Bertie,
And-
before we go any deeper in this, because we have a whole hour to get to dig in, I wanted to address some of the other comments and questions that on the chat.
And
So
yeah, those are the questions, but I know I really want to try to get good clean data, or at least as clean as possible to deal with when I'm doing this analysis. It takes a while to do, you see.
absolutely. So I just wanted to comment, first of all, something which Derek pointed out, which I did too quickly, so you didn't see what I was doing. And I wanted to make sure people know that when you first upload a punch, you're going to see nothing because you're too zoomed in. So what I did very quickly, and you probably missed, was I clicked on reset view. And that's the quick way to get out to your full field of view to see the punch data. The second thing is, well, the grayscale, and we can talk about that during the long hour if you want. And Craig's pointing out the conformal mapping is maybe not quite right in the J-Helio viewer. Robert, the PAM data is not, well, I'm going to let Marcus answer, but just to say, well, I guess I already told you that the FITS file, oh, I know what I wanted to tell you. The JPEGs that are out there now are all the clear, and eventually we're going to have JPEGs for polarized brightness. But if you want to, when the PAM data becomes available, because I don't know how quickly, Marcus, we're going to get the polarized brightness in JPEG 2000 format, but you can do it with the FITS file. If you pull off a two-dimensional layer, and I'll make in the IDL part of the codes, I'll put my data reader as well as my flatten code. And I believe, Marcus, you're going to put a flatten code out too that would allow you to pull off a layer and look at polarized brightness. Because right now you have to do that before you can make a movie like this in polarized brightness. And it's quite interesting to look at the difference. And you can also, I've started playing around with doing the ratios on that as well. And I think Kurt has as well. Yeah, so Pam's going to be moving out. When do we think, Marcus? Okay.
I don't really want to make a promise date because we need to validate to make sure that the PAM is of good quality first. So we don't want to give you something that is very confusing and has the wrong polarization measurements. So we will say soon, and Craig is saying real soon. So
excellent. All right, other questions about J-Helio viewer, and then I'm going to open it up for all sorts of questions. Dave, yes.
Yeah, I have a question. I assume you can save these J-Helio viewer things as movies, right?
Yes, you go like this.
MP4, probably. Movies.
Pardon?
Can you save these as MP4 movies?
Yep, I just did. So
Okay.
if you make a movie like this and then you just go, it puts it in a, I find it by going into my Finder, typing in J-Helio. It finds the master folder. I look in exports, and that's where it is.
And these can get really huge, I suppose. I wonder if there's a way of
Well, I'll tell you, it was
reducing the size, averaging or something.
and 10 megabytes. It's not terrible.
Yeah, okay. Okay.
Okay, other questions before I stop sharing this one? All right, so let me stop presenting. And at this point, let's open the floor to all sorts of questions. I'll keep the recording going for at least a while we're still having questions, but if we kind of go into a mode of people working independently and just doing occasional questions, I'll turn off the recording. But so let's kind of say thank you to everybody who's here, who needs to go. But if you want to stay and keep asking questions, we absolutely encourage it. And we're here for another 45 minutes. Before I sign that part off, let me actually pass it to first Marcus and then Craig to see if they have any final words. Marcus?
I'm just excited that we're getting this far along in the processing and excited people are starting to use the data more. So thank you all for coming.
And Craig?
There we go. I will echo everyone's sentiment that this is a real triumph from the SOC. Looking at these images, it's easy to forget just the amount of sophisticated processing that has gone into making 4 spacecraft, or even just 3 of them in the mosaics right now. act like a single spacecraft, and an extraordinarily well-calibrated one at that. So we clearly have some room to go, but as I pointed out to the SOC, we're clearly in the home stretch now. We're now delivering data that are comparable to or better than anything you've seen in the past from stereo. And as you could see from the stack plots that Ritesh showed, there is still structure left in the residuals, and therefore there's more work we can do. So we're extremely close. We have climbed, if you will, we've just summited K2, but there's one more peak to go. So I'm pretty excited about that, and I'm very excited to have everyone using the data. I will admonish folks, please do look at the nomenclature guidelines in Sarah's paper or in the Punch overview paper, and try to stick to them. Something I really want to encourage in our community as we start analyzing the data and pumping out papers using them is that we try and settle on a uniform mode of speech. In the past, we've often seen parts of the solar community suffer confusion over vocabulary or over geometries and analytic approaches that just aren't compatible, but really mean the same thing. And so to the degree that we can, let's try and keep everything consistent. With that, go forth and be productive. Have fun. Back to you, Sarah.
Mhm. Okay, I will turn off the recording, but please keep asking questions. Can't figure out how to turn off the recording.
Question, Sarah.
Mhm.
So I assume all these links and so forth that are in the chat